Now I will tell you about the secrets of history that you will not find in any history textbook. Before us lies the American West, covered in deep snow. The wind blows relentlessly, and the temperature drops to unimaginable lows. In the middle of this icy ocean stands a lone log cabin, a fragile wooden box. Inside is a family of settlers, and the only thing separating them from freezing to death is a few logs, some dirt, and a fire in the hearth. Many of these first dwellings were built hastily, with minimal tools and even less experience. They were full of cracks, drafty, and the fireplaces drew more heat than they gave. Surviving in such conditions seemed impossible. However, they survived, using not brute force, but remarkable engineering ingenuity. Watch the video to the end to learn how one simple trick using ordinary mud could make a log cabin almost airtight, and why the largest fireplace was often a settler's biggest mistake. What I am about to tell you will completely change your perception of survival in the Wild West. When a settler built a cabin, his main enemy was not the cold wind itself. His enemies were three invisible physical processes, three thieves who stole precious heat from his home. Victory or defeat in this war was determined not by the amount of firewood, but by how well the structure of the house resisted these three threats. Understanding this was the first step to survival. The first thief was called thermal conductivity. This is the ability of heat to literally pass through solid objects. If you touch a metal object in the cold, it instantly takes away your heat. Settlers intuitively understood this and chose wood as their primary building material. Wood, thanks to its porous structure with millions of air pockets, is a poor conductor of heat and therefore a good insulator. However, logs alone were only half the solution. Thermal conductivity became a major problem in places where wood came into contact with stone, such as in the foundation or near the hearth. Stone conducts heat very well, and without proper insulation, it could act as a bridge through which heat from the house escaped directly into the frozen ground. Therefore, experienced builders tried to minimize the contact between the internal wooden structures and the stone foundation. But even thick log walls were not a panacea. If the logs were damp, their thermal conductivity increased dramatically. The water inside the wood froze, turning the insulating material into a conductor of cold. Therefore, it was vital to use dry, seasoned wood and protect the walls from moisture. This was the first line of defense in the battle against an invisible enemy. The second and most aggressive thief was called convection. This is the process by which heat is transferred by moving air. Simply put, it is a draft. Cold air is heavier than warm air, so it always looks for the slightest crack at the bottom of the house to get inside. It flowed under the door, between the floor logs, and through cracks in the walls, creating an icy stream at your feet. Once inside, this cold air pushed the precious warm air upward. The warm air, being lighter, rose to the ceiling and sought any way out. It escaped through cracks in the roof and, most tragically, flew out through the huge hole that was the chimney. Thus, the hut turned into a pump that actively pumped itself out of warmth, replacing it with icy air from the street. The settlers felt this enemy literally with their skin. They saw the candle flame flicker from the invisible movement of the air and felt the cold creeping across the floor. Every unsealed crack was an open door for this thief. Fighting convection was the dirtiest and most tedious job, requiring constant attention and repairs. The third thief was called radiation. Heat is also infrared waves emitted by any warm object, be it a fire, a stove, or a person. This thermal radiation travels in a straight line and is absorbed by colder objects. In a log cabin, the interior surfaces of the walls were very cold in winter. Even if there was no draft in the room, a person sitting near the wall felt cold. Their own heat jumped from their body to the icy wall. The fire in the hearth also radiated heat, but much of it simply escaped and was absorbed by the cold stones of the chimney or the walls instead of warming the people in the room. Combating this type of loss was the most difficult. It required not just sealing, but creating barriers that could reflect the heat back into the room. Intuitively, settlers solved this problem by covering the walls with fabrics or skins, creating an additional layer that heated up and radiated heat back instead of absorbing it. Thus, building a warm hut was a real engineering challenge. Settlers had to overcome thermal conductivity by choosing the right materials. They had to stifle convection by sealing every crack, and they had to reflect radiation by controlling the interior surfaces. Which of these three heat thieves do you think was the most insidious and difficult to overcome in frontier conditions? Share your opinion in the comments. Are you ready to learn the truth about why the smartest settlers built their first homes literally underground? Before cutting down the first tree, a settler made a decision that could determine the outcome of his struggle for warmth. It was a decision about where to build. The choice of location was not a matter of beautiful views, but the first and foremost engineering calculation. An experienced builder sought natural protection from the strongest enemy, the prevailing winter wind. On the Great Plains, this was the merciless north wind. Therefore, the ideal location was the southern slope of a hill or ravine. The hill served as a giant shield that deflected the icy air currents upward above the roof of the hut, significantly reducing heat loss from convection. The location of the house relative to the sun was the second most important factor. They tried to orient the hut with the facade, where most of the windows were, facing south. In winter, the sun is low on the horizon, and its rays could shine directly into the windows almost all day long. It was a free heating system, known today as passive solar heating. The heat that entered the house was absorbed by the floor and walls and slowly released back at night. They also avoided building in low-lying areas and at the bottom of valleys. Settlers noticed that such places were always colder. They intuitively understood that cold air is heavier and, like water, flows to the lowest points of the landscape, forming pockets of frost. Building even on a small hill just a few meters above the valley floor could mean a difference of several critical degrees. But what if there were no hills or trees around? On the endless plains where there was no natural protection from the wind and no wood for construction, settlers turned to the oldest and most reliable insulator, the earth itself. They used the main building material that was abundant under their feet. This is how one of the most common and effective dwellings of the early frontier appeared: the dugout or dugout. It was not so much a building as a space dug into the ground. For its construction, a steep riverbank, ravine slope, or hill was chosen. A room of the required size was dug horizontally into the slope. The process was laborious but simple. Using shovels and pickaxes, the settlers dug into the dense soil, creating a living space. The walls of this space were made of compacted earth. The only built part was the facade, the front wall, which was usually made of logs, turf, or stones, if they could be found. An entrance and possibly a small window were made in this wall. The roof was made of logs or branches, which were laid on top of the dugout room and then covered with a thick layer of earth and turf. Over time, grass grew on this roof, and the dwelling almost completely blended into the landscape. It was the perfect camouflage, but its main purpose was insulation. The secret to the effectiveness of the dugout lay in a phenomenon we now call geothermal energy. The Earth, at a depth of only a few meters, has a relatively constant temperature throughout the year. In northern latitudes, this temperature remains around 10 to 12 degrees Celsius. When a blizzard raged outside and the temperature dropped to -30, the walls of the dugout remained at a stable +10. The earth did not heat the house, but it did not cool it as much as the air did. The temperature difference that had to be compensated for by the stove was not 40 degrees, but only 10. This was a huge saving in firewood and heat. The dugout was the absolute champion in the fight against all three heat thieves. A thick layer of soil completely blocked convection. There were no drafts in the dugout. It had enormous thermal conductivity inside itself, but also enormous thermal mass, stabilizing the temperature. And it completely stopped radiation losses. It was not just a dwelling, but an engineering masterpiece born of necessity. However primitive it may seem, from a thermal engineering point of view, it was almost perfect. Was it ingenious engineering or an act of desperation? But what if you were building not a dugout, but a log cabin in the middle of the forest? You had walls, but they were full of holes. In the next chapter, we will reveal the secrets of mud armor, which sealed log cabins and turned them from sieves into thermoses. The secret I am about to reveal was literally held together with mud and sticks, but it was valued more than gold on the frontier. You can build a cabin out of the thickest logs, but without this secret, it will remain nothing more than a drafty shed. A log house is not just logs stacked on top of each other. It is a complex system, and its most important element was mud armor, or a process known as shanking. The problem was obvious. No matter how straight the logs were, they never fit together perfectly. There were always gaps between them, sometimes several centimeters wide. These gaps were the main gateway for enemy number one, convection. The wind whistled through them, blowing out the heat and bringing in snow dust. The settler's task was to seal these gaps tightly. The sealing process consisted of two stages, which are often confused. The first stage was the chopping itself. It consisted of filling the large gaps between the logs with solid material. To do this, they used whatever was at hand: wood chips, bark fragments, small stones, or even dry moss. This material was tightly packed into the gaps to create a solid foundation for the next layer. This first layer was structural. It was not airtight, but it created a framework on which everything else would rest. Experienced builders knew that if they simply filled a large hole with clay, it would inevitably crack and fall out. The solid filler was reinforcement that gave the entire structure rigidity and durability. The second stage was called dubbing, or in our terms, coating. This was the very mud armor. A viscous plastic mortar was applied over the solid filler, sealing all the tiny pores and cracks. The composition of this mortar determined whether the house would be warm. Simple mud and water would not do here. The recipe for the perfect plaster was a valuable secret, passed down from one settler to another. Clay always served as the base. Clay had the necessary plasticity and stickiness to adhere well to wood and stone. However, pure clay shrunk significantly when it dried and became covered with deep cracks, which again opened the way for drafts. To combat cracking, a thinner was added to the clay, usually sand. Sand reduced shrinkage and made the mortar more durable. But clay with sand was fragile. It needed reinforcement, just as concrete needs steel reinforcement. This reinforcing element was the filler. Any fibrous material that could be found was used as a filler. Chopped straw or hay was ideal. These fibers, mixed with clay and sand, created a composite material similar to adobe. It was strong, elastic, and hardly cracked at all. If there was no straw, dry grass, wood shavings, or any similar material was used. The application process was difficult and dirty. The mixture was kneaded with the feet in a special pit until the desired consistency was achieved. Then, without tools, this mass was manually packed into the gaps on top of the shanking. It was applied both inside and outside, creating a continuous, airtight layer. The builder's hands were constantly in cold, sticky slurry, but it was a necessary job. The biggest problem with this technology was maintenance. The mud armor was not permanent. The wooden log house constantly breathed. The logs dried out, swelled from moisture, and settled under their own weight. This movement led to new cracks in the coating. Every fall, before the onset of cold weather, the settlers had to carefully inspect their homes and repair any defects that had appeared. It was a never-ending battle for airtightness, but it was worth it. A well-caulked and plastered hut was transformed from a drafty sieve into an almost airtight cocoon. Heat loss from convection was reduced tenfold. What if I told you that everything you thought you knew about the romantic fireplace in a cabin is wrong? We are used to imagining life on the frontier with a large, roaring fire in a stone hearth. This image seems to symbolize comfort and warmth. But from a heat engineering point of view, the The classic fireplace was a catastrophically inefficient device. It was a real wood eater, often cooling the house more than it heated it. The main problem was its design. An open hearth requires a huge amount of air to burn. In order for the wood to burn brightly, the fireplace had to draw in hundreds of cubic meters of air per hour. And it did not take this air from the street, but from the room itself, which it was supposed to heat. This process created a powerful draft. All the cracks that the settler had worked so hard to seal began to work twice as hard. Cold street air whistled into the house, only to be immediately consumed by the fire. A paradox arose. The stronger the fire burned in the fireplace, the stronger the draft blew at your feet. The settlers were well aware of this effect. They described how they had to sit literally close to the fire, burning their faces, while their backs were covered with frost from the icy draft. The fireplace created a tiny comfort zone within a radius of 1 meter, but made the rest of the room unbearably cold. The second engineering miscalculation was heat loss through the chimney. The chimney for the fireplace had to be wide to provide draft and remove all the smoke. But along with the smoke, the most valuable thing, hot air, also escaped through this pipe. According to estimates, up to 90% of the heat generated by burning wood simply flew out. It was like heating the street. Settlers spent weeks preparing firewood, cutting down trees, sawing them, chopping them, and drying them. And then 9 out of 10 logs burned in vain, heating the sky above the prairie. The efficiency of such heating was depressingly low, but in early huts there was often no other choice. The fireplace was primarily needed for cooking and as a source of light. Its heating function was secondary and far from optimal. Nevertheless, settlers tried to get the most out of it. They built fireplaces out of stone or clay, materials with high thermal mass. The idea was that the massive stone walls of the hearth would slowly heat up from the fire. The stone stored heat like a battery. Then when the fire died down at night, the heated stones would slowly release this heat back into the room. This smoothed out temperature fluctuations somewhat, but did not solve the main problem: the enormous consumption of firewood in constant drafts. More advanced fireplace designs, such as the Ramford fireplace, attempted to improve the situation by changing the shape of the firebox. It was made shallower, and the side walls were placed at an angle. This helped to reflect more radiant heat into the room rather than into the chimney. But these were complex devices, inaccessible to most people. Therefore, for many settlers, life in winter turned into an endless struggle for fuel. The whole family worked only to feed the insatiable monster in the wall. It became clear that a completely different approach was needed for effective heating. A technology was needed that could lock in the fire. So how did they solve the problem of pumping heat out of their own homes? The solution came not from stone, but from metal. In the next chapter, we'll talk about a real revolution in heating huts, the advent of the cast iron stove, which changed everything. The solution to the problem of the insatiable fireplace was a technology that began its triumphant march across America in the 19th century. It was a freestanding cast iron stove. For a settler on the frontier, the purchase of such a stove was an event that divided life into before and after. It was not just an improvement, it was a real technological revolution that changed everyday life and increased the chances of survival. The main and fundamental difference between a stove and a fireplace was that it was a closed system. The fire burned inside a metal box. This simple change immediately solved two major problems. First, the air for combustion was not supplied by an uncontrolled flow, but through a special small opening, a blower or damper. Controlling the air supply was a brilliant engineering move. Settlers could regulate the intensity of the flame. By closing the damper, they reduced the flow of oxygen, and the wood stopped burning fiercely. It began to smolder slowly. The same amount of wood that burned in an hour in a fireplace could give off heat for 5 or 6 hours in a stove. Fuel consumption was reduced significantly. Secondly, the stove solved the problem of heat loss. Hot gases did not escape immediately into the wide chimney. They circulated inside the stove, giving off their heat to its metal walls. The stove body itself, becoming red hot, began to radiate heat in all directions, 360 degrees. The room warmed up evenly, not just in one spot in front of the fire. Even the chimney pipe that came out of the stove was not a loss, but an additional radiator. It was usually run across the entire room, and sometimes through the attic before being let outside. Passing through the pipe, the hot smoke continued to give off heat to the metal, and the metal to the air in the room. As a result, the smoke that exited the house was already significantly cooled. The efficiency of such a system was remarkable. While the best fireplace barely reached 15% efficiency, a simple cast iron stove easily achieved 50% or even 70%. This meant that 3 to 4 times less firewood was needed to heat the same house. This freed up a tremendous amount of time and energy. In addition, the stove was much safer. A closed fire meant that sparks did not fly onto the wooden floor or bedding. The risk of fire, which was a constant threat in wooden huts, was significantly reduced. This made it possible to leave the stove smoldering even at night, maintaining a minimum above zero temperature in the house. Stoves varied. The simplest ones, which settlers could afford at first, were often made of sheet iron. They were lightweight and could be transported in a wagon, but they burned out quickly. Heavy cast iron stoves were truly valuable. Cast iron stored heat well and lasted for decades. Popular models such as the Franklin or Potbelly became the center of life in the cabin. The family gathered around them, clothes were dried on them, and a coffee pot or pot of food was always placed on their flat-top surface. The stove took on the function of both heating and cooking, completely replacing the archaic fireplace. This metal box was not just a household item. It was a symbol of progress and control over the elements. It allowed settlers not only to survive at the limits of their capabilities, but to live in relative comfort. The ability to maintain stable heat in the home changed everything, from health to morale. Of course, the stove also cost money. It had to be purchased and delivered, which was an adventure in itself on the frontier. But those who could afford it gained a decisive advantage. They won the war against the cold thanks to sophisticated engineering encased in cast iron. I will reveal the best-kept secret. The real enemy in a cabin was often not hidden in the walls or the roof, but under your feet. Settlers could insulate their walls perfectly and install an efficient stove, but still suffer from the cold. The reason was simple: the floor. The laws of physics are inexorable. Cold air always sinks, turning the floor into the coldest area in the house. In the earliest and most primitive dwellings, built in haste, there was no floor as such. It was simply compacted earth. This solution was quick and required no materials, but in winter it was disastrous. The earth froze to a great depth and became a giant accumulator of cold. This earthen floor literally sucked the heat out of the room. Any warm air that came into contact with it immediately cooled down. Moreover, in spring or during thaws, such a floor turned into mud. It was a source of dampness, and humid air always feels colder and requires more energy to heat. It quickly became clear that a barrier between the living space and the frozen ground was needed. This is how the first type of wooden flooring, the panshan floor, appeared. Its construction did not require lumber, which was not available on the frontier. The settlers felled trees and sawed the logs into logs of the required length. Then each log was split in half. This resulted in pieces with one flat side and one round side. These planks were laid on the ground with the flat side up, as close together as possible. The round side either lay on the ground or was dug in slightly for stability. This was a huge improvement over an earthen floor. Wood, as we remember, is a poor conductor of heat. It created a barrier between the cold ground and the settlers' feet. Walking on such a floor was incomparably warmer and more comfortable. It also solved the problem of dirt and dampness, raising the standard of living to new heights. However, plank flooring had its drawbacks. No matter how tightly the logs were laid, there were still gaps between them. Cold air from under the house still penetrated through these gaps. The floor was warmer, but drafts at foot level remained a serious problem. The next step in the evolution was flooring on joists. This was a more complex engineering solution. Settlers laid several thick support logs on the ground. On top of them, they laid the same planks or, if possible, real boards. This was a radical improvement. The secret of this method was the creation of an air gap. There was now a space filled with still air between the cold ground and the floorboards. This still air is an excellent insulator in itself. It prevented the cold from the ground from reaching the floor. This is the same principle used in modern insulation or double-glazed windows. The settlers intuitively discovered one of the fundamental principles of thermal insulation. This air gap under the floor became a decisive factor in the fight for warm feet. Of course, there was still the problem of drafts, which were already blowing through this underground space. To stop them, the settlers resorted to a trick. They filled in the foundation of the hut from the outside. In the fall, they piled up a high mound of earth, peat, dry leaves, or turf against the outer walls of the house. This barricade closed all the gaps and prevented the wind from blowing under the floor. But even with wooden floors and a mound, there were still gaps between the boards. How did they deal with them? And what did they do with the windows, which were just holes in the wall? In the next chapter, we will look at the small tricks of internal defense that were of great importance for preserving heat. We've talked a lot about log cabins, but in the vast expanses of the Great Plains, in Nebraska, Kansas, Dakota, settlers had a different problem. There were no forests here. For hundreds of kilometers around, there was not a single tree suitable for construction. But under their feet was another equally perfect building material: earth, more precisely, sod. This is how the most unique dwelling of the American frontier was born: the sod house. It was not just a house on the ground, it was a house built from the ground. And from a thermal engineering point of view, it was one of the most ingenious solutions that could have been devised. Its insulating properties were legendary. The top layer of prairie soil served as the building material. This soil was densely intertwined with the roots of tall grasses that had grown there for millennia. These roots were so strong that settlers joked that you can only plow the land if you stand on the plow with all your weight. But it was this very strength that made sod the ideal brick. Using a special plow, settlers cut the sod into long strips resembling ribbons. These ribbons were then cut with an axe into standard-sized bricks. These prairie bricks were heavy, strong, and most importantly, completely free. The grass roots inside them acted as natural reinforcement, preventing them from falling apart. These sod bricks were used to build walls, just like regular bricks. They were laid in 2 or even 3 rows so that the joints did not coincide. The result was a monolithic wall with a thickness of 60 centimeters to 1 meter. Such thickness was unthinkable for wooden construction, but it was the norm for a sod house. It was this incredible thickness that was the secret to thermal efficiency. A turf wall had what engineers call high thermal mass. This meant that it was able to absorb, store, and slowly release a huge amount of heat. It worked like a giant battery. In winter, the frost could not break through such a wall. It took weeks of continuous cold weather to cool a meter-thick layer of earth. The inner surface of the wall almost always remained warm, close to the temperature inside the house. Heat loss through thermal conductivity and radiation was minimized. In summer, the opposite effect occurred. While it was 40 degrees outside, it was cool inside the sod house. The walls absorbed excess heat, preventing it from penetrating inside. Soddy was a natural air conditioner. Settlers claimed that their homes were cool in summer and warm in winter. The roof was usually made of the few logs that could be obtained or from branches. It was also covered with a layer of turf on top. This made the house virtually invulnerable to the wind. No draft could penetrate the meter-thick walls of compressed earth. The problem of convection was solved once and for all. Of course, such houses had their drawbacks. The roofs often leaked during heavy rains. The walls could crumble if they were not stacked correctly. But in terms of heating, it was almost the perfect dwelling. Very little fuel was needed to heat such a house. Often dried dung or even twisted bundles of tall grass were used as fuel instead of firewood, which was not available. What would have burned without a trace in a log cabin, without giving off any heat, allowed a comfortable temperature to be maintained in an airtight turf house. The turf house is the highest manifestation of engineering thought based on the use of local materials. It was a triumph of the use what you have principle. The settlers did not fight nature, but used its main resource, the earth, to create an almost perfect thermal fortress. So the settler built walls, laid a floor, and installed a stove. It would seem that the house was ready for winter, but now a micro-war began. A battle with hundreds of small gaps through which heat continued to escape. The main enemies at this stage were windows and doors. Each of them was a potential hole in the thermal armor of the house. Windows in early huts were a luxury. Glass was incredibly expensive and fragile, and it was almost impossible to deliver it intact. Therefore, the first windows were simply cutouts in the wall. To close them, settlers used a variety of materials. In winter, this opening could simply be covered with a wooden shutter, plunging the room into complete darkness. A more advanced solution was oiled paper. Settlers took thick paper, or sometimes thin fabric, and impregnated it with fat or wax. This material became translucent, allowing a little dim light to pass through, but more importantly, it did not let the wind through. It was the first membrane to protect against drafts. Of course, such a window was a terrible insulator. Heat escaped through it almost unhindered. Therefore, at night or during heavy snowstorms, the windows were always closed additionally. Heavy wooden shutters were hung on them from the outside, and from the inside, the opening was covered with thick fabric. Textiles became the main weapon in internal defense. Any fabrics that were in the house were put to use. Old blankets, burlap, rugs, all of this was hung on the walls, especially on the coldest northern wall. This created an additional air gap, which sharply reduced heat loss. A wall covered with fabric felt much warmer to the touch than bare logs. It did not draw heat from people. It was a simple and effective way to combat heat radiation. The room immediately became cozier and warmer, even though the air temperature may not have changed. Special attention was paid to doors. The door was the largest moving part of the house and the main source of drafts. It was made of thick boards, but no matter how tightly it was fitted to the jamb, there were still gaps. The gap under the door, at floor level, was particularly large. To combat this threshold draft, the settlers invented a simple device that is still in use today. It was a long fabric roller filled with sand, sawdust, or simply rags. This sausage roller was tightly placed along the bottom of the door and effectively blocked the flow of cold air. The floors also needed to be insulated. Even a good wooden floor on joists was still colder than the rest of the air in the room. To solve this problem, the floors were covered with anything that could provide an extra layer of insulation. Homemade rag rugs woven from old clothes were used. These rugs not only made the floor warmer to the touch, but also trapped the cold air that could seep between the boards. They worked as an extra layer of insulation. In a house where there was not a single extra degree, each such rug was worth its weight in gold. All of this internal defense was aimed at one goal: to create a cocoon of several layers inside the house. The outer walls fought the wind. The mud armor sealed the cracks. And the inner layer of fabrics and rugs created the last line of defense, keeping precious heat as close to the people as possible. We have already mentioned that the settlers intuitively used materials with high thermal mass. But what does that actually mean? It was one of the most subtle and ingenious engineering techniques, which allowed them to stabilize the temperature in the hut and save fuel. The idea was to use stone or clay as a heat battery. Materials such as wood are good insulators. They do not conduct heat well, but they also do not store it well. They heat up quickly and cool down just as quickly. Stone or clay, on the other hand, are poor insulators. They heat up slowly, but once heated, they can retain a huge amount of thermal energy for many hours. In early huts, where there were no stoves, this role was performed by a massive stone hearth. Although it was ineffective as a heater, it was excellent as a heat accumulator. All day long, while the fire burned in the hearth for cooking, The giant mass of stone slowly and deeply heated up. By nightfall, when the fire died down, the most interesting part began. The air in the hut should have cooled down within an hour, but that didn't happen. The hot stones of the hearth began to slowly radiate the heat accumulated during the day back into the room. It was a gentle, pleasant warmth that kept the temperature in the house above freezing until morning. Thus, the fireplace was not just a stove, but a complex two-phase system. During the day, it worked in charging mode, absorbing excess energy from the fire. At night, it switched to discharge mode, giving off heat and preventing the house from freezing. It was a low-tech but very effective way to manage thermal cycles. Settlers who understood this principle used it everywhere. Even when efficient cast iron stoves appeared, they did not abandon stone. The stove quickly heated the air, but cooled down just as quickly as soon as the wood burned out. To solve this problem, the stove was lined with stones or bricks. These stones did not prevent the stove from heating the air, but they absorbed some of its intense heat. They smoothed out temperature peaks, preventing the room from overheating. And when the stove began to cool down, the stones came into play and continued to heat the room for several more hours. It was an ideal hybrid system, rapid heating from metal and slow storage from stone. In some huts, more complex designs could be seen. For example, the chimney from the stove did not go straight up, but through a special horizontal bore-off made of stones and clay, which ran along the wall. This bore-off, similar to a bench, was, in fact, a heat exchanger. Hot smoke passing through this labyrinth transferred its heat to the stones before escaping into the chimney. The entire structure heated up and turned into one large warm radiator. This was an incredibly efficient use of heat that would otherwise have been lost. This heat battery principle was the key to stability. It transformed the house from a box subject to sudden temperature changes into a massive stabilizer. Even if the fire went out for several hours, the house held the heat. This gave the settlers a reserve of time and reduced overall fuel consumption. The use of thermal mass was an invisible but critically important technology. It did not require complex materials, only an understanding of how different substances work. It was pure physics in the service of survival. The last and perhaps most important engineering trick of the settlers had nothing to do with walls, smoke, or earth. It was a trick related to behavior. The settlers on the frontier quickly realized one simple truth. In conditions of fuel shortage, it is impossible to heat the entire house. That would be an unaffordable luxury. Instead of trying to raise the temperature throughout the entire space of the cabin, they employed a strategy of heat zoning. They did not heat the house, they heated people. This was a conscious decision to refrain from heating unused cubic meters of air and to concentrate all efforts on creating small but warm islands of life. The center of such an island was, of course, the stove. All life in the hut in winter was compressed into a small circle around this cast iron hearth. Here stood the table where they ate. Here the women sat doing needlework. Here in the evening, everyone gathered to simply be together in the warm zone. The corners of the room, especially those near the outer walls, could remain freezing cold. People only went there when necessary. No one wasted firewood to make these corners comfortable. It was a pragmatic and efficient allocation of resources. This zoning strategy was especially evident at night. Sleeping places were the most valuable objects in the house, and their location was carefully thought out. Beds were never placed near the outer walls, where they were exposed to cold and drafts. They were moved as close to the stove as possible, but the main invention was the box bed or canopy bed. Settlers surrounded their sleeping places with heavy curtains made of any fabric available. This created a room within a room. The small enclosed space under the canopy was much easier to heat. The heat from the breath of several sleeping people and the residual heat from the stove was trapped inside this fabric box. The temperature inside could be 10 to 15 degrees higher than in the rest of the room. This allowed them to sleep in relative warmth, even when it was freezing outside the thin fabric of the hut. All household processes also followed this logic. Cooking, especially baking bread, required a long and hot fire. This work was always planned for the coldest time of the day, such as early morning. The oven, heated for baking, simultaneously provided the maximum amount of heat, warming the house at the beginning of the day Washing or laundry, which involved a large amount of evaporating water, was also done at a strictly designated time. Water evaporation greatly cools the air, so they tried to do this quickly while the oven was working at maximum capacity. Thus, the entire life of a settler in winter was a dance around the heat source. It was a daily, hourly engineering task of managing heat flows. They moved furniture, hung fabrics, planned their day, all for one purpose: to concentrate every precious degree where it was needed most. This was not passive defense, but active management of their microclimate. This behavioral strategy was as important a tool for survival as an axe or a gun. It proved that engineering is not just about materials, but also how we use them. We can see that a log cabin on the frontier was not just a shelter. It was a complex engineering machine designed for one purpose: to retain heat. Without degrees or textbooks, the settlers mastered the fundamental laws of thermal engineering through practice. They learned to combat thermal conductivity, stifle convection, and reflect radiation. They used the earth as an ideal insulator in dugouts and sod houses. They turned ordinary mud and grass into mud armor that sealed the walls. They realized the inefficiency of an open chimney and revolutionized their homes by placing a cast iron stove in the center. Every action they took was dictated by logic and experience. These hidden heat tricks, from choosing the right location to beds with canopies, were the sum of thousands of small decisions that ultimately meant the difference between life and freezing to death. This is not a story of suffering, but of the triumph of human ingenuity over the elements. What other topics from the history of the American frontier would you be interested in? Perhaps you want to know how they built the first cities on the prairie, or how they obtained water in arid regions? Suggest topics for future videos in the comments, and don't forget to subscribe to our channel so you don't miss new stories about survival and engineering of the past.